That's perfect, Andy.
Okay, there we are. Okay. So good afternoon, everyone. I've talked in the past to the Building Design Association, I think probably about 10 years ago when it was down in Hobart, up in Coffs Harbour. And even that 12, 13 years ago, we started talking about condensation, but now it's really sort of raised its head in terms of regulation and the degree of issues around here. So in the past, I might have talked about condensation conundrums and all the issues, but today I want to talk more about the salvation and the solution. And I do see the audience today, building designers, you hold the key to that solution through good design and understanding. Okay, just get out of the way, just so you know who Procter Group is, so you can be very skeptical from the outset, because we're going to talk about issues. We do have the products to solve them, so I want you to know that from the outset rather than discover it when you go home this evening. So we're very much involved in construction membranes, vapor permeable, vapor closed, a whole range of insulation from stone walls, XPS, PIRs, vacuum panels, trickle ventilation systems, acoustics, and everything around sort of the area of sort of indoor environmental quality, all the bits that go into the building you can't see from the inside to the outside, but help ensure that the building performs as you wish. Okay, just another thing, what we've been doing over here, do make a note of this. During the lockdown, we've been working quite hard on our system solutions library. So on the website now with our parent company, DC Tech, I think we're currently about 60 design solutions. We've gone through different standard roof wall floor build-ups all around the different types, and we've assessed it for the main climate zones, tropical, temperate, and cool climate zones, about what's suitable and what works. So we come up with some robust designs and how they work depending on what you want to achieve. So there's a good resource which we've looked at for designs for Australia. Okay, what I'm going to talk about today is generally what condensation is, what causes it, and what the control strategies are. This is some of the changes within the National Constructions Code, both in Volume 1 and 2. Talk a bit about external insulation rain screens, different types of membranes, some of the modelling which we look at to determine and predict condensation risk, and some discussions on indoor air quality and how that relates to condensation. So just back in 2018, we realized that construction management was going to make its way into the National Construction Code for the first time in 2019. So both in Volume 1 and Volume 2, so Part 247 within the residential code. So this gentleman from the ABCB, what he's actually saying now is condensation's come into the code. At this point, he says, yes, there are some deemed to satisfy measures in there. You can follow the deemed to satisfy, you need to follow the deemed to satisfy, but that's not necessarily going to solve all the issues. They're pretty lame measures. I wouldn't say they're very challenging. Hopefully these are what they're asking to do in the code in terms of ventilation, use of membranes, you all be doing anyway. But I think there are more changes and more guidance, particularly with relation to how to deal with roof systems on the way within the next iterations of the code. The reason we managed to get in the code was there's a huge body of work done based on a survey commissioned by the Australian Building Codes Board into condensation, which they put out in, I think, 2015, and was one of the best responded surveys the Buildings Code have ever done. 4,000 responses. What they came back was that over about 40% of new buildings, particularly in the residential space, have mold and condensation problems. There's a real issue out here. It's no longer about saying, you know, it should be right. It's not happening out there. It is happening out there. I don't think we need to spend half an hour going through evidence of what is going in there. It's an extensive issue, and that's why it's now gone from non-mandatory guidance into part of the mandatory code. So you'll be looking at the inside of a window down in Melbourne. So what's happening is during winter, you have a cold piece of glass. We have high levels of vapor pressure and humidity inside the building that comes in contact with the glass and condenses. Where I'm today up in Sydney, we got the same issue here through the winter as well. Condensation happening on the inside of the glass. If we've got any readers up in the tropics and you've got a well-conditioned space, you might get condensation on the outside of the glass because you've got high humidity condensing on the cold surface side. So here's a little quote from Tim Law, who put into the submission to the Parliamentary Inquiry into biotoxin-related illness, and I think this relates to a lot of issues we have around in construction. Say, well, yes, we do have a problem. So there is an important problem to solve in our buildings, and everybody is sure that somebody will fix it. Anybody could do it, but nobody does. Somebody got angry about it because it's everybody's job. Everybody thinks that anyone could do it, but nobody realizes that everybody won't do it. In the end, everyone blames somebody when nobody does what anybody could do. And I think that's a pretty fair summary of what I've been going through in the sort of past 13 years since I moved to this Australia. It's a bit of a blame game and an avoidance of responsibility. So when I'm having conversations with them about condensation, I try to work out where I'm talking to is where we are in terms of condensation grief. Now, we may be familiar with the stages of grief: denial, anger, bargaining, depression, acceptance. And it's really the same thing as a journey which we all go through in terms of our understanding of condensation and getting out to acceptance at the end. So we've heard it all since the beginning. There's a photograph from Sydney of a roof space, tiled roof space, no ventilation, condensation pouring down on the side of a foil-based sarking. You know, it's not Australia, should be right. It doesn't happen here. Must be photographs from overseas. And then when you go through dial, then there's this case of anger and think, well, geez, I've just been doing what the guides told me to do, or what the code said to me. It's not my fault you get angry. It must be down to energy efficiency. We're building housing too tight, or blaming the codes board, or blaming the manufacturers. And there's a period of anger. You'll eventually get through that period of anger and then start, you know, the bargaining phase. And if you're down in Tasmania, I think you're saying, oh, it's a Darwin problem. If you're Darwin, you're saying it's a Canberra problem. If you're Canberra, you're saying it's like a Sydney problem. Or you think, well, geez, I've done it. And you've got so much invested in your career over X number of years building things, and realize maybe some of the things you've done in the past could have caused an issue. So if you continue to do them, they're more likely to cause issues now. You just really have to accept that. So we have these conversations. Well, what if I use the fall with the holes in it, or the fall face blanket, chuck a vent on the roof, all sorts of just minor tweaks, when really it needs to be a real sort of wholesale approach to fixing the system, rather than to compromise and try and bargain to get a solution. Then you think, well, you go away, do a bit more research, look at some overseas work. You may have been caught out in the case, or you got a client who's got an issue, and you go through, you know, depression. Really, this is bad. It's just too hard. Do I leave the profession, or change my job? You know, that's my partner's name. But eventually, very quickly, hopefully, you'll get onto the stage of acceptance and realize this isn't actually that hard. It's not like we're trying to, you know, build up in, you know, northern Scandinavia or really severe climate zones. All the solutions are here. The rest of the world has gone through and solved these issues. It doesn't necessarily be that expensive. A lot of the fixes are quite simple. So I'd worked in Japan in the UK, and when I came here in 2007, pretty much everyone was in denial about condensation. We knew, looking at the climate data, we knew, looking at build types and standard construction, there must be issues out here, but, you know, it was just complete denial. Whereas I would say around about this stage, in terms of who I'm talking to, the majority of people that we talk to around there have accepted there's an issue and are really into that phase of design to resolve the issue. Still a fair bit of bargaining goes on, and there will be sort of deniers, and the deniers won't move in the scale until the code changes and moves them up that pathway. So understand why we might be seeing more problems now than we did in the past is that the really moisture is it's a matter of balance. So what I'm not suggesting is that one day it gets to 8 degrees outside, and then suddenly every building in, you know, the eastern states of Australia is going to fall down because of mold and corrosion. It's really there's a sort of tipping point about the degree to which these problems will occur. So first, if we think about capacity to store moisture. So this is what we call hydric buffering capacity. So if you think about old building, a lot of timber and masonry, you could throw a lot of water at that, and it can safely absorb that, and hopefully during periods of the day and potentially dry that out. But as we move towards lightweight construction, away from timber to steel, and from mass to lightweight construction, there's very little storage within our building envelope to manage those peaks and bodies and drying potential. And also in terms of the moisture source, we are seeing quite high levels of humidity inside the building. So changes in lifestyle, occupancy, greater levels of occupancy, less ventilation. So we are seeing high levels of humidity. So we got a combination of reducing our hydraulic buffering capacity. We're adding more moisture into buildings, lifestyles, but also we've reduced the ability of our buildings to dry. And that means we said, well, we've gone through energy efficiency, and it's all been about blocking up the, blocking up vents, tightening up the buildings. It's just by good building practice and better materials, we're actually seeing buildings dry a little bit better. So we've reached a sort of tipping point now where problems are more likely to occur. So understand anything about condensation today, we need to understand that it could be the reasons why we have condensation. We see buildings, issues in buildings could be one of three things. And it could be that we have high levels of moisture, levels which are too high, too much humidity in the building. That could be lack of ventilation, or it could be a leak, for instance, or subfloor moisture entering the building. Or we have temperatures in the building fabric which are too low, and very often it's a combination where we've got like high levels of moisture from airflow passing through the building envelope, reaching those cold surfaces and condensing. So we'll go through some of these causes and some of the solutions, but let's understand what condensation is and why it happens. So if we're in a room at say 23 degrees and 50% relative humidity, which is around about this time of year, it's fairly reasonable and comfortable place where you want to be. And if we bring in a beer at say 4 or 5 degrees centigrade, what's happening here is that the beer is at 5 degrees, so that the air surrounding that beer glass is cooled by the glass, which is 5 degrees, and air at a cold temperature can't hold as much vapor as a gas and starts releasing as a liquid. So what you see on the side of the glass is not beer, which is leaking out of the glass, so there's no point in licking it. So it's like the distilled sweat and breath of whoever's sitting next to you in the pub there. So what's happening as you cool that body of air down, relative humidity goes up. You've got the same absolute quantity of moisture in that air, but as it cools down, relative humidity rises. And it rises until it reaches what we call dew point. So that's when the air can't hold the water as a gas anymore, and that's where it reaches 100% relative humidity, which would be about 12 degrees. So that's a good number to keep in your mind, is that if we're typically at 50, 23, well, it's when surfaces start to get to 12 degrees in the temperate and the cool climates that condensation likely form on those surfaces, and that starts as a thin film of air. If we actually sort of demonstrate what's going on here, we've got a jug of water. And what we're showing here is this is it's half full. So assuming this body of air is at 23 degrees centigrade, the water, we've got half of it quite safely in here as a liquid. Now, if we bring along, we try and cool that body down to air which can hold less. So this air is at 12 degrees. And then we fill up this body of air with the same amount of water that's in the air. What we do is we get to 100% relative humidity. So that's why we're getting to dew point, and that's when you get that thin film of air. Now, if we try to cool this further down, say for example 5 degrees, we start to fill that up very quickly. We're 100% humidity, and then this is condensation. This is more condensation, more and more, and this is coming out of there and it's coming out into the building, condensing on surfaces and getting stored within with material in your building. So we think again after a few nights on the beer, yes, when you're halfway, think about this now, when you're having a beer, when you're halfway down the glass, you'll see that condensation stops forming on the top half, and that's because that's returned to ambient temperature and dew point is no longer happening. But in the meantime, after five or six beers, and it's on a beer mat, what you'll see is that within the building, you've got porous materials, and they store the moisture. So your soggy beer mat then tonight is your plasterboard, is your insulation, it's your timber, moisture getting stored in those spaces. Now it's important to realize that it doesn't need to get to dew point before you've got issues. Even when it's getting down to say 15 degrees, that brings the air down to 80% relative humidity. And at that degree of relative humidity, you've still got the ample opportunity for mold to germinate and for mold to grow. Admittedly, not as fast if it was say 95%, but you've got a chance for mold to grow at this point. So really, what I want to talk about is how condensation relates to control. So since we stepped out of the swamp. The reason we don't sort of live outside in the wide open is we want to create an environment which we control. So we started living in caves and trying to heat the caves. And then we have to think about, oh, what do we do? We started thinking about waterproofing and insulation and ways of doing that. And that's probably one of the original vapor permeable roofs you can see there. And then there's issues of security, how we're protecting ourselves. And then we look about, well, okay, we're protecting ourselves, but I want a bit of daylight in here, want a bit of fresh air. So we start putting windows into our buildings. And then we can, instead of fires, we got light, we got electric lights. And now we're at the extent now where can have remotely complete control over our built environment in terms of temperature, humidity, security, all these issues. So it's been quite an evolution. That's all really about.
Excuse me, Andy, sorry to stop you there. We're just getting a few issues with your voice or your audio. Could you just make sure you sit a little bit closer to the audio, and perhaps, I think, try and sit as still as you can, because it seems to be cutting in and out.
Okay.
All right, thanks very much.
See, here we go. So really what I don't want to do today is just say, well, this is the way you must do things. I'm not a control freak. I'm not going to tell you the exact way to do things. If anything today, I want you to understand that it's down to you as designers. You become the control layer freak. So if you understand what control layers do and how to place them within the building, then you can discover there's many solutions to the same issue. So we think about the key control layers. We have our air control layers to stop air moving through materials. We have our thermal control layers, which is essentially the insulation, so we can maintain thermal comfort without using too much energy. We've got a water control layer, so that's to stop water from entering the building. So that's our external cladding. Acoustic control layers to stop sound escaping or sound getting in, or absorbing sound within the space. And then less well understood would be the vapor control layers, or management of vapor through layers through diffusion. So some materials allow vapor to pass through, and some are vapor barriers which don't allow vapor to pass through. And then we also have our fire control layers, again, to stop the spread of fire inside to outside the building through passive control to stop fire, passing through and spreading or coming back into the building. So we think about probably two of the most common issues we see in both the temperate and the cool climates of Australia. And we realize that condensation is not just about using the right type of membrane. It's also about where we locate our insulation. So we look at the top issue where we've got a single leaf masonry wall and we've got the insulation on the inside. Now this blue line shows temperature as we're running through from inside at 23 right to 6 degrees on the outside. Insulation does its job, causes the temperature to drop. This dotted blue line we see here now shows what dew point is. The inside that dew point is 12 degrees. But as we go through the building envelope, the temperature where it meets the dew point line is on the back of the first cold condensing surface, which is the inside of the concrete. Now in the past, when we had no insulation, we kept the surface of that wall, of that concrete above dew point by heating it by convection on the inside. As we added more insulation, there's no drying potential. We're not using energy inside the building to dry that out or keep it above dew point. So that's, and then we look at the other with the lightweight construction. There's been a habit all across Australia just to use a vapor barrier, a piece of aluminium foil on the outside of our buildings. It's been there to create a radiant air barrier, but now we fill that space with insulation, so we're getting nothing from the radiant barriers, but also the insulation is cooling down that radiant barrier so it's now at outside temperature rather than inside temperature. And any kind of climate where you're getting condensation inside of your windows, you're going to start to get condensation on the inside of the foil vapor barrier. So really, at the top issue, what we've got, we're dealing with. When we got mass construction is the thermal insulation where it's placed relative to the structure. And we look at lightweight construction, we've got our water control layer, which is the cladding and the sarking. Sarking is essentially a secondary water control layer. What we've done is we've managed water ingress, but we've used the wrong type of vapor control. So in that location, we should be using something that's vapor permeable rather than a vapor barrier. So you can see how we're involving lots of different control layers. So really, when we look at the cause of condensation, it's really here by the temperature in the building fabrics are too low. So the back of the tilt-up concrete, or we've got the flow of vapor to these cold surfaces, and we create those cold surfaces by the insulation. So we think first, let's address thermal control layers and insulation. Now here we're looking at both internal and external insulations. Internal insulation on the left, this is the red line is showing the temperature profile on the hottest day of the year, say it's 40 degrees, and that plots the profile through the wall, outside left to inside on the right. And on the coldest day of the year, when it's -1, for example. And you think, well, those walls, both systems, both have the same R value. They both will comply, but they both can perform very differently. So if we actually look at what happens if we're looking at the temperature of the structure, so when you insulate externally, the temperature of that concrete structure is determined day by day, hour by hour, month by outside temperature. When we insulate externally, we've got a very stable temperature of our concrete, and that's determined by indoor temperature, and we keep our indoor temperatures stable. So we're not having to heat up and cool down that thermal mass. So insulated thermal mass is great in terms of performance, for energy performance. But then also when we look at what happens with the cold temperatures and dew point, when we insulate internally, we create a dew point on the inside of the concrete, the structure. But when we insulate externally, the temperature of your concrete never falls below dew point because it's determined by inside temperature. So we can manage condensation by insulating externally, and that's one of the most robust processes. And you'll see in these designs, there's no use of any membranes at all. It's just about where we shifted the insulation. Certainly, if you're going to be working in the commercial space where in the future where you have to take account for thermal bridging, you'll find that the R value of our roof and wall constructions is going to have to start accounting for thermal bridging. So all sorts of systems where you can do external insulation with rain screen bracketry system, continuous external insulation. Great for designs for energy efficiency and condensation management. So on our tech library, we've got all the systems available to allow good quantities of external non-combustible insulation or combustible insulation within the single-story building space. So we then look at water and vapor control, how that relates to condensation management, and go through some typical wall types we might see. So we look at wall type 1 and think, well, what kind of climate might we be doing this? So on the outside, we've got a vapor permeable wrap. So one of these the textile products that we and others do. So what we've got is drying potential from inside towards the outside. Now on the inside of the wall, we've put a vapor barrier, like a plastic sheet, a vapor retarder, or an aluminium foil, or a non-permeable insulation. So what we're doing there is stopping vapor from entering into the wall construction. So this is the kind of thing you might be doing if you're designing a swimming pool in most of the cool temperate climates, or if you're in alpine, Tasmania or Canberra type climates, where even the most vapor permeable wall wrap out there is not enough. You're also trying to stop vapor from getting into the wall through air movement and diffusion into the wall construction. Now, if we look up at the tropics in conditioned buildings. So outside during the wet season, the dew point of outside air might be as high as 25, 26 degrees. So if you're cooling your building on the inside of the tropics down to below 25 and you open the window, outside air will come in and condense on your conditioned surfaces. So everything about the tropics is trying to get something vapor tight and airtight on the outside to stop that vapor from entering in, and make sure that anything on the inside is vapor open. So any moisture that is in your wall can quite safely dry into the building where you're hopefully doing some dehumidifying. So what you got is to understand that if we look at the majority of climates, you can have just your vapor permeable on the outside and your plasterboard on the inside. This is what someone might call like a breathable wall. It's not a breathable wall, it's a completely airtight wall. We've got 3 different airtight layers there. What is it? It's this wall with drying potential for all seasons. So there you've got drying potential towards the outside in the winter, and if need be, you've got drying potential towards the inside if conditions permit. So really, when I've gone around all the climates of Australia over the years, I've only seen pretty much a design, it's about 10 years ago, whether it was Darwin or Tasmania, everyone was wrapping up the building with a piece of aluminium foil, probably not without a cavity. You've got to realize that you've got to design for climate. It can't work for all climates, and that explains why we're having so many issues. So we've had the first version of the condensation handbook came out in 2011. I think we're about the third or fourth version now. We've had the scoping study in condensation, the extent of the problem, but there's been inquiry into biotoxin-related illness in our buildings at the House of Representatives, and now condensation management into the National Construction Code. So things have reached there. So some of the key changes that hopefully you're familiar with have come into the 2019 code relate to some of these issues. So really it is about managing risk. So the ABC are very clearly saying that deemed to satisfy is not going to solve the problem. There's still responsibility on design to understand your climate, the materials you're using, and how you manage these risks. And it's not doesn't sit in energy efficiency. It's not related to basics or Section J or anything like that. It's really, it comes under health and immunity, because what we're trying to do is provide a healthy and comfortable environment for occupants. And we have moisture issues caused by condensation that has a massive impact on the health of the occupants. And there are a lot of people in Australia suffering from health just by poor indoor environmental and indoor air quality. So some of the key deemed satisfy measures relate to our water control layers or vapor control layers, and also air in terms of the ventilation strategy. So first, let's look at the key one regarding pliable building membranes. So if you are using a pliable building membrane and you're in climate zone 6, 7, and 8, then that now needs to be vapor permeable. The new standard for issued in 2017 for 4,200 now, actually you have to quantify the degree of vapor permeance or vapor resistance, and you have a clear classification for vapor permeance. Now that's not to say I still think you need to be using vapor permeable in zones 4, 4, and 5, so it hasn't gone all the way, and I think certainly it should be a vapor permeable class 4 type of membrane as well. You should be going as vapor permeable as possible. Now, how do these types of these products work? They work because usually got sort of pores in them. So you have for example, water is a molecule is very high molecular size, so that would be the soccer ball. But as a vapor, it's just one H2O, and that can pass through. That's very small molecular size. So the vapor would be the golf balls, and the water would be the soccer ball there. Now, interestingly, it got through. There is a loophole. It's one of the most sort of depressing things is that there is a loophole, and a lot of the big suppliers out there of fall and sarkings have actually provided documents to actually guide people and step them through to take that loophole, and that for me is quite depressing. So this is a photograph of a building down in Melbourne where you've got a vapor permeable membrane on the top floor, and you have like a sarking on the ground floor. Sarking on the floor would be this. It's like a fall. I can see through this. There are holes punctured in it. Now, what has happened is that the code has redefined a pliable building membrane as one of which is watertight. So if the sarking, which is there to be watertight, if it's no longer watertight, stick a pitchfork through it. Doesn't need to then be vapor permeable. So you've got a brick veneer situation down in the ground floor where they've used fall with holes, and on the top floor vapor permeable, just to save themselves around 10-15%. So why? It's just it's pretty sad. So we have to look not just at the issue of the numbers. It's also about resilience of the building. So we look at timber construction. Here's some work which CSR Bradford do, who distribute our products, but also still continue to sell foil with holes. They put a lump of timber in a bucket of water, so it's got up to 70% moisture content. Wrapped it up with a vapor barrier foil. Wrapped it up with one of the foil with holes, and wrapped it up with a Procter vapor permeable membrane. What you can see is vapor permeable. After 4 weeks, it's dried out, whereas the vapor barrier, after 6 months, it's still, upwards of 65% moisture content. Interesting, if you look at the fall with the holes, which everyone sort of calls the breather, is being called out there. 6 months, it took 6 months for that to get to 20% moisture content. And if you know that the timber needs to stay below 20% moisture content, or you get timber rot. So these products, they got holes in them, so they're not watertight. because there's insulation going in behind them, they're not providing the function of vapor barrier anymore, and they're certainly not vapor permeable enough or watertight. So I don't know what functionality they provide other than to hold the insulation in place. You may as well use a fishing net. So these deemed satisfying measures, what are they trying to address? So they're trying to address the situation where you've got your lightweight construction with your insulation and a vapor barrier on the outside with dew point reaching condensation. So we actually changed that vapor barrier over to something which is vapor permeable. The vapor can pass through the vapor permeable membrane where it can safely drain and dry away within your cavity. So there was lots of non-mandatory guidance out there within the ABCB handbook, 2014, particularly all these sort of areas which I've made red. They're highlighting condensation can form inside impermeable wraps or panels that cool to indoor dew point. And if you remember earlier on, typically your indoor dew point might be around about 12 degrees. So all these, you do all these kind of things in climate zones where the temperature of those impermeable materials are going to get below 12 degrees. You got to understand that's why you've got interstitial condensation in the building envelope. That's the science. Even in Australia, the science applies, and it applied in the United States in 1938. So one of the early building science papers here from Rogers is looking here at what happened with lightweight construction when they started using reflective insulation, reflective sarking products, and then put insulation behind them. So suddenly they did this big change in dynamic, and they had moisture issues and wondering, well, is it the fault of the foil? Is it the fault of the insulation? It's just, there's nothing wrong with each of those products. It's just they've been located and used together in the wrong climate for what we're trying to achieve. So we're almost about 100 years, and we're going through the same issues here in Australia. So in terms of deemed to satisfy the resolution, what we've got is our internal lining, which is our air control layer. We're adding our insulation, which provides the thermal comfort and acoustics. And then we're water control layers, external cladding, and the vapor permeable sarking. So we draw the temperature profile, same dew point analysis, steady state. What we've got is an airtight construction, watertight with drying potential in both directions. And if anyone's working in the commercial space requiring type A, type B construction, the 2016 version of the code said that all parts of that element had to be non-combustible. So there was an issue that there was no non-combustible vapor permeable sarking material out there. So a lot of people go into like vapor barriers or back pan and causing moisture related issues. Now that has been addressed with the 2019 code, and that provided your sarking material is no greater than 1 millimeter and has a flammable index no greater than 5, so that's the S1530 Part 2 test. So there are plenty of products out there in terms of now vapor permeable where we can do that in a type A, type B construction, high-rise construction. The reason behind that is that really the sarking at that thickness is not providing much combustible content. So here's a photograph of our sarking used in a full-scale fire test, which had insulation on the outside and cavity barriers. So you think, well, they are combustible. It is polypropylene. You light it, it's going to shoot up the side of the facade, but that's not necessarily going to happen. It's really about the whole design, but it's about their combustible content as well. So in terms of the code changes, who's not going to be impacted by it, or who is impacted by it, particularly if you're in zones 6, 7, 8, so Western Sydney, requirement to use vapor permeable. I'm driving around here and still seeing plenty of foil used on buildings, unfortunately. If you're down in Victoria, pretty much most of the populated areas, zone 6, 7, 8, Tasmania, there, Canberra. So certainly the cooler zones need to be using vapor permeable, and a lot of designs were using these anyway. So if you're out there and you don't like reading labels or you can't read labels, then this is important. You need to understand what is a vapor permeable membrane, what's a vapor barrier membrane, and we'll say it on the packet. Now on this building, again, not to pick on people in Victoria, but this is a photograph from Victoria. So this section here, we got a vapor barrier, off the shelf fall vapor barrier. The blue Proctor here, that's one of our products, but it's a product which we normally put on the inside of the installation, particularly for swimming pool environments, whereas there is a vapor barrier. We certainly wouldn't be recommending this construction. And they've used one of our roof vapor permeable sarkings on this section. So we have 3 different types of product. If I was feeling in a generous mood, I said, well, they were building right on the board between zone 5 and zone 6, and trying to be very precise, but I don't think any of us believe that's the case. It's just what's left over here. The performance of sarking and permits is important to understand. If you're a closet, say a roof space venter, you need to change your habits. Highlight the please no more venting of bathrooms into your roof space. That's included in condensation management. Who's not impacted by code changes. So if you're what we call a leader and reader who've been understanding this stuff over the years, maybe in one of the past presentations and using vapor permeable products, it should be no change for you. Most buildings have roofs. Now there is no deemed to satisfy requirements or measures in the code in terms of what type of sarking material to use in your roof space or how to insulate. So that's a missing space. And I would say that most of the severe problems we've come across in condensation in Australia have been in the roof space, because huge amounts of vapor are going through very vapor open ceilings and condensing on cold sarking or cold materials or cold roof battens or materials in touch with cold roof spaces. That's where low pitch roofs, that's where so many of the serious problems are. It becomes very evident because it drops down onto the ceiling and we got water coming through the ceiling and moldy plasterboard. So that hopefully needs to be addressed in the next version of the NCC. Okay, so deemed to satisfy fairly easy. There is a verification method which looks at modeling. So everything we've shown so far is what we call steady state modeling at one point in time, temperature and dew point. The verification method also considers solar radiation, rainfall, but also is an iterative process that goes through and calculates this hour by over a period of time. The software we use is called WUFI. So if we'd run that earlier case of internal external installation with a concrete construction, we'll fly through here five years worth of climate data, and what it does, it spits out a result at the end of the day that you can say at any point in that building envelope what's been happening. So in the case where we insulated externally, very quickly you can see that it was drying out. But when we insulate externally, every winter we're getting that peak in moisture content of the insulation, and worryingly that year on year that peak is increasing. So that's an indication that's not bad. And that's local climate data, local materials, hour by hour analysis of what's going on. It's as good as model as we can get. Now you can also then pick a point within the wall, look at the type of material, and run a mold analysis on the back of the concrete. There we're seeing within a year, 2 years, we're right up red light evidence that mold is going to occur. That's a mold risk. So this is where it comes into the impact on the health and amenity of your occupants. So this can all be modeled now in terms of the verification method. We tend to use this more often to point out bad design than rather to because the deemed to satisfy is so easy, why would you look at this? Now, air tightness and ventilation is very important in terms of condensation management. So we look at our different control layers again. Air control layer is very important in terms of thermal, also with acoustic. So airborne acoustic noise travels through holes in air tightness. Also very much related to vapor. So vapor passes in huge quantities through air leakage. Water, when we use a lot of water as barriers to create a pressure equalized rain screen, but if that barrier is not airtight, then you don't get the same. So water will fall through the holes where there's air leakage. And then also in terms of passive fire control, air tightness is fire will pass through holes and non-combustible materials too. So air tightness is very important. So often we hear is that now houses need to breathe. Now, really, a house is an inanimate object. It doesn't breathe. A house needs to perspire. Doesn't quite sound as great to the marketing people, but houses, they don't need to breathe. They can be airtight. People need to breathe. So when we look at the physiology, really, the building envelope is really about how we think about in terms of our skin, how we manage our comfort, evaporation, sweating, transport, shading, perspiration, and the ventilation systems, how we breathe, the physical, how we remove polluted air or humid air, and how we breathe, and the movement of air in terms of the ventilation systems. So when we think about air control, is a lot of our occupants, a lot of your customers think you've got a magic air machine that's stuck on the wall. You press the button and it creates fresh air into the building. When it's not, your split systems are actually recircling air, so they're actually bringing in fresh air. And the tendency is that, oh, we whack on the air conditioning, that costs money, so the occupants will close the window. And air gets recycled, CO2 levels increase as you go along. It's not a magic air creating machine, it's an air conditioner. So understand why ventilation plays an important role. If we look at outside air and inside air, so we think summer conditions, June 9 o'clock, we've got 83% relative humidity. On the inside, you're 50% relative humidity. You think, well, geez, it must be the outside air is more humid. You think, well, I don't open the window because we're letting in air at 83% relative humidity. But in reality, when we look at the psychometric chart again in terms of outside and indoor air, so what we've got on the outside is 83 degrees, 8.3. The dew point of that would be about sort of 5.6 degrees. That's when you start seeing dew on the ground. Now, what happens is we actually bring that air into the building. We have to heat it up, but as we heat it up, we've got the same moisture content, but we reduce the level of relative humidity. So if on the inside we're looking at that 23 and 50, the dew point is higher at 12 degrees. That's when we start to see condensation on the inside of our windows. Now you see that red line, the horizontal line, is a moisture content of 9 grams per kilo as opposed to 6 for outside air. So really we've got higher levels of absolute humidity on the inside of the building than we have on the outside. The reason for that is everything that air is on the inside of the building used to be outside. We brought it into the building, but then we add moisture to it, and we add moisture by sweating, by breathing, by drying our clothes, by creating the moisture. And that's why when we think about our ventilation strategy, we try to remove that moisture at source, from above the oven range, from our showers, from the bathroom, from the laundry. That actually comes out, and we need to actually replace that with outside air. So we're both diluting the pollutants, but also diluting. And there is an energy penalty because that outside air needs to be heated up, unless you go for heat recovery or ventilation or energy recovery ventilation and use the vented air that's going outside to heat up and condition the air which is coming in. So really what we're talking about here is managing the levels of moisture levels. So we got high levels of extraordinary levels of relative humidity inside our buildings in Australia, and that's for a number of reasons. We don't have normal 24-hour mechanical ventilation. Now there is going to be a requirement now within the code now for minimum rates of ventilation down to your bathroom, your laundry, and your kitchen, and particularly they need to be vented towards the outside. There are requirements now for ventilation of the roof spaces in terms of both ridge and eaves ventilation. Eaves ventilation is very important so that when we take air out of the ridge, it's replaced by outside air and not air that you've spent money to condition on the inside through the downlights. But you only need to ventilate roof space if you are one of those closet roof space ventilators and you really just can't get away from venting your bathroom and your roof space. Then you need to meet these requirements for ventilation in the roof space. Hopefully in the future, I think we're going to start ventilating all our roof space, certainly in the cool and temperate climate zones. So opera windows, it's very easy to comply with natural ventilation by having opera windows, regardless of whether they're an awning that's open only so far or they're never opened. If we look at this building here, very few of those are getting actually natural ventilation. The rest of them are closed. They're not getting ventilation. So yeah, opening windows, we know when it starts to smell bad or it gets musty, you open the window, the fresh air, you dry it out, and it becomes comfortable. So the question is, why don't we open a window? Okay, sometimes it's perfectly reasonable not to open a window. It could be too cold on the outside. It could be too hot. It could be raining. There could be bushfires and pollutants outside. We're worried about security. You live on the ground floor. It could be loud outside. Acoustic problems. It could be too windy. You could be worried about the noise it makes when the blinds flap around. It could be pollution on the outside. You're worried about insects and rodents. Or you just think, well, geez, it's too expensive to condition this air which is coming in. So lots of valid reasons why you can't open a window. And this is a very important part of bringing a relative humidity in down, is being able to look at ventilation systems that do that. So I used to work in Japan in 2003 to manage the stick house problem. They mandated that you have to have some kind of 24-hour mechanical ventilation. That could be balance, supply, and exhaust. It could be supply air, so you positively pressurize. It's great for the tropical climate zones, or it could be a mechanical exhaust, where you take the humid air out of the bathroom, but you bring in that replacement air through passive vents, particularly in new windows. So really, in terms of cost, that type of 3 approach, where you use the existing vents in your bathrooms, instead they run 24/7, cost $2 a month to run, like DC, very, very quiet, just running all the time, just to take the moisture out. They run faster when it gets humidity on the side, but it's always bringing in a certain amount of air change. You had to demonstrate you were getting an air change rate of 0.5 per hour, so changing that body of air once every 2 hours. And the vast majority, 79% of that, still uses that type of system. Type 1, the red wares, where you've got balanced heat recovery. So these types of products, trickle vents, are now becoming more common in Australia, but also the 24-hour mechanical exhaust vents, 4 watts, very, very quiet. So these types of products do exist here, and there are discussions about looking at better ways mandating 24-hour ventilation systems. One of the issues with trickle vents is that when it does get cold, occupants, certainly from my UK experience, when it gets cold, trickle vents get closed off, never get opened up again. The product came across in Japan was passively managing that, so that when it got too cold, the vent would close off to a degree, and then when it was warmed up to ambient temperature that was comfortable, it would open back up again. So you're doing everything you can to minimize people interfering with passive makeup air, or interfering with 24-hour systems. So in terms of CO2, we really need to be maintaining at least levels below 800. So outside CO2 is typically about 400. But even my crappy apartment in Sydney, you can see just there early on, I've opened the window, purged the air, but it doesn't take very, very long before that CO2 level rises back up again. So unless I'm keeping the window open all the time, I'm not able to manage air quality in terms of CO2, but that's also an indicator of pollutants, VOC, and humidity levels. So when we're trying now with the requirements, we should be talking about when we do blower door testing, getting 50 pascals, air change rates about 10 and below, or permeance rates within the building envelope of 10. You can see from overseas, when you hit a target, you never just get right on the target. So it's trying to aim. If we say that once we get to levels under blower test of, say, once we get below 7, we really need to be thinking about 24-hour mechanical ventilation. It's very hard if you're design something from between 10 and 7. So if you aim for 10, you're likely to get down to 6, 7, 8. So even like decent wrapping up the building with a tape, with the perma wrap, you can reasonably expect to get down to levels of 3 or 4. So we really, when we look about air tightness, we need to be thinking that in conjunction with some system of mechanical ventilation. So that could be an approach where it's exhaust plus passive air makeup up, or in areas where cooler areas where the payback period is heat recovery, and those types of systems. So when we think about what's lying ahead in terms of ventilation control, is we need to really think about better exhaust vents in the bathroom, which are running continuously, passive makeup air, heat recovery systems, but also that's you now have some phones which have got air quality sensors. Certainly during the bushfires earlier on in the year, there was a big uptake in sales of air quality meters measuring PM 2.5s and VOCs. So if we're spending upwards of $1 million on a property, and we're in there after 6 months, and we find it's unhealthy, and we start measuring this kind of stuff, we're going to be, well, why do we spend this money? But we're living in an environment which is really impacting on our health. So this type of measurement is going to be readily accessible in terms of understanding and managing a controlled environment. So we need to have buildings which can passively perform and maintain those decent, reasonable, acceptable levels of air quality. So just to bring things into conclusion, in your role in terms of control layers and managing condensation, we use a lot of control layers in the building envelope, so we've got to understand their functionality. So, for example, is this type of sarking, what's its function? Is it watertight? Is it airtight? Is it diffusion open? what's his fire properties, what's his, thermal insulation properties. So understanding what functionality we want out of that control layer, then quantifying it. And then when we look at our drawings, well, here's our vapor control layer, here's our vapor kernel membrane, here's our airtight layer, and where these lines cross, are we creating a potential conflict of interest between these different control layers, and identifying that at the design stage, because once you're through construction and you spot it, it's very hard to resolve. So understand the function you want, quantify it, be very firm about that specification, so you can manage that, so that these products are installed, designed, and function as you intended. So in terms of back to round things up, why we call it condensation salvation is that the design stage, the products are out there, the modeling is out there, but at a design stage, you need to be able to understand that, and we need to work together as designers, as suppliers, as installers to resolve this. So we finish off, and I take a different take on the previous I said here. So there is an important problem to solve in our buildings. At the moment, nobody's sure that anyone will fix it. Anybody could do it, so somebody does. No one gets angry about that because it's everybody's job. Nobody thinks that someone else will fix it for them because everybody realizes that anyone can fix it. In the end, no one has to blame somebody because everyone does what anyone can do. So I think we'll open the floor to some questions.
Got some questions now coming in, Andy.
Okay, did the sound get better?
Sound got a lot better.
Thank you.
Thank you. So the first one is, how does passive house fit into the breathing building?
Okay. So if that was a question earlier on the presentation, hopefully I addressed that in the latter part. So having an airtight envelope such as passive house allows you that control. So if your building envelope is leaky in terms of it's all about infiltration and gaps, it's very difficult to control, thermal, it's difficult to control air quality, it's different to control ventilation. So in a passive house, you're certainly looking there at a requirement for a 24-hour system to manage air quality. So the building envelope is managing all those things like thermal comfort and moisture within the building envelope. A building doesn't breathe. You don't suck fresh air in through the wall. That fresh air in comes through ventilation strategies. So it allows you, at the moment, if we've got very leaky buildings, it's all about infiltration. You've got no control about the quality of air, where that air is coming from, how it's managed. If you've got a tight envelope, then you can manage air quality through ventilation. So don't build tight unless you're considering how to ventilate right. They have to come together. If we just build tight and we ignore ventilation, we're going to get ourselves in a lot of problems.
Andy, we've got another question. Can you recommend a monitoring system that is economical for clients' houses, but that we can also maybe get data from?
If it's monitoring and it's readily accessible, don't know, lots of brands on there if you check on eBay, but the things that you can really readily get that have got tracking, you want to be looking at your temperature, you want to be looking at relative humidity. Those are your standard sensors you can get. But then also looking at CO2 levels. So CO2 levels are a good proxy for air quality because it tells you whether you're getting that required amount of air change. Then it's certainly, I would say that having a PM 2.5 is useful. So if you're certainly living in the city and you're worried about outside air quality or bushfire, your particles, we pay a bit extra. I've got one which does VOC at home, which means that if we bring home some furniture from IKEA and put that in the room, VOC shoots up and the thing goes off red, and the kids refuse to sleep in the room until it's gone back down. But I would say as a minimum, temperature, relative humidity, CO2, and particle meters. So yeah, probably a little sensor there with trackability, $250. And my kids certainly learn about the environment, so they now know as you take that outside, it falls back down. They learn how to manage the room. They know what happens when you open the window. They know when to do that. They know when something's burning in the kitchen and creating particles.
Andy, before we go to the next question, we're going to put up the BDAA QR code for the members to be able to scan and record the session. Now, also for non-members, you will receive the, sorry, can you hear me? You will, yep. For non-members, you will be receiving a certificate of your attendance in an email. So, Andy, we've got another question. We're going to go live to Darren Evans. Darren, could you ask your question, please?
Hi, Andy. Great presentation. Just got a question. When you're talking about venting roof spaces and the requirements are now going to be pushing further down that path, how do we deal with that with the fire-prone areas, building in fire-prone areas, and more of our buildings are being controlled in that manner? How do we balance that out?
I don't have an insight about where things are going in terms of the code, but in terms of practical recommendations, roof space ventilation is, I think, is a good solution for most Australian climates. It's great for dumping out hot air in the summer and managing condensation in the winter. A lot of the roof space issues, some of the photographs have showed they are from bushfire zones. So a lot of some photographs from Victoria from the Black Saturday bushfires, when a lot of those buildings were rebuilt. And a lot of the sort of flame zone roof applications have really tightened things up. So they were using a lot of non-combustible insulation into the gaps and the holes to stop the embers coming into the roof space. So ventilation can be effective. Roof space ventilation, you do require to have your non-combustible mesh with a maximum 2 mil aperture on there to stop the embers from getting in. Now, I believe that certainly someone in the BDAA for New South Wales, there's look at a standard, or BDAA producing a standard detail for flame zones for managing both condensation risk and moisture. So certainly new products come out there. The products which are vapor permeable sarkings, which have got they're maybe not non-combustible but have limited combustibility. So there are different products out there managing that. But effective ventilation systems, you can, when we had, was working in Japan with ease vents, you'd have ease vents with intumescence. In the case of a big fire, that would close them up. So there are lots of passive ways of managing that, but yeah, stopping your embers from getting into the roof space, and those measures do exist. But in terms of flame zone, trying to get a vapor permeable roof space. So we're certainly looking at vapor permeable sheathing boards and limited combustibility membranes to manage that space.
Thank you, Andy, and thank you, Darren, for the question. Just to let everybody know, Brickworks will be doing a presentation next. I've put the link there into the chat group, so if you want to click on that link. Andy, we've got one more question for you from Jesse. Jesse, if you'd like to ask Andy a question.
Jesse's on mute.
Yes. You there, Jesse? Okay. Well, we've got another question. Any suggestions for condensation on glass, given it's hard to control the temperature difference and dew point, or is this a ventilation solution? Obviously double glazing the go, but for current houses with low E, for example. This is by Anonymous.
Okay, so hello, Mr. Anonymous. So it comes back to the three causes of condensation. Either you got surfaces which are too cold or cold below dew point. So that's where you address in terms of using double glazing, triple glazing, or better glazing systems. So instead of the inside of glass being determined by outside temperature, it's insulated to a degree. Also thermally broken window frames. So that's in terms of managing your cold surfaces. But then also, if you've got high levels of relative humidity, the condensation will start to happen at a higher temperature and will happen to a greater degree. So if you actually reduce your levels of absolute humidity in the living space, then condensation will occur less. So yeah, effective ventilation, and ironically, one of those solutions is by opening the window. So if you're seeing condensation on your window, that's probably an indication you've got high level of humidity in your room. Then it's maybe time to dilute with some outside air. So yeah, double glazing and managing relative humidity inside the space.
That's pretty much it there, Andy.
There you go.
From the BDAA, we'd really like to thank you very much for your support and presenting today. We wish you a pleasant weekend. And just to let all those non-members know, we are holding a special. We're waiving the $100 admin fee. If anyone would like to become a member of the BDAA, go to the BDAA website, click under membership and become a member and register your interest, and we'll ensure that you get your $100 admin fee discount. Thanks very much, Andy.
Thank you.